All right, not strong enough to keep molecules from moving past each other. What did you think about that? Okay, does A sound super wrong? No, so let's kind of keep that in mind. It might be A, but then let's look on. B, strong enough to hold molecules relatively close together, but not strong enough to keep molecules from moving past each other. That sounds a lot better, right? So the answer is B, probably. You should always double check. Very weak compared with kinetic energies of the molecules. No, that would describe a gas. Okay, gas, they're moving fast, so they're not going to hang out with each other. Strong enough to hold molecules relatively close together. That's sort of close, but not better than B. Strong enough to keep the molecules confined to vibrating about their fixed lattice points. That's a complicated definition of a solid, is what E is. So B was the best answer of all the options there. Okay, not too hard, I hope. Okay, let's come to this slide. All right, so this is just from a website obviously made decades ago, but that's all right. We don't need to worry about anything below number 2. But will you have a short discussion with your lab partner how you would answer and what you would answer for number 1 and number 2? Go ahead and do that for a second. Thank you. I didn't even realize I was there. I thought the Windows ink was on for some reason. All right, so if anyone's ever watching this most people think it's A, and we definitely learn. Sad and a cry face. I love this. This answer is not correct. The boiling point depends on molecular mass and intermolecular interactions. I think that you felt since this was the largest molecule, it would have the highest boiling point. Okay? Unless there is a large difference in mass, it is the least important consideration. Now, it is important, but there was other things. Think about what causes intermolecular interactions and select another answer. Okay, we'll do this like they vote in Ireland. So, it's called ranking. Ranked choice voting, and it's genius, and we should do it in America. It would change the world. Anyway, so all of you that selected A, you now have to re-vote. Will you have another conversation and cast the next vote? All right, so internet people, if anyone ever watches this, the majority of class chose letter D. Am I still on? I am. Oh my gosh! Wow. I don't know what squiggly face means. You guys are the emoji generation, so you can tell me. But this answer is not correct. Hydrogen bonding is the principal intermolecular attraction when a compound has an electropositive hydrogen atom and an available non-bonding electron pairs. Ooh, what does that mean? Although fluorine is more electronegative than oxygen, there are no HF bonds in this compound. All right? Now this is tricky. It sure looks like there was, right? It looked like there was. You're like, this is hydrogen bonding. But if you draw this molecule out, it's a C surrounded with 4 things. C, H, H, and F, and F. We'll put the F's up here. And these are H's. All right? F's not bonded to H, it's bonded to C. So in letter D, there is no hydrogen bonding. Okay, so we'll rank choice now. Everyone has to re-vote. Will you have a short conversation and get ready to cast your vote in 20 seconds? So let's get ready to vote. Don't be afraid to vote. Everyone's been wrong so far, so don't feel dumb. You're all dumb together. So here we go. Who thinks it's B? Raise your hands. 4 of you, 5 of you think it's B. Who thinks it's C? All right, the majority picked C, so we'll click on C next. Smiley face emoji. Oh, finally, we are a happy camper with a cute little nose. All right, you are correct. All right, the reason you're correct is because of hydrogen bonding. C, H, 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 O, H. That, and there might have been two, I don't remember, but there was an OH, right, on the end? Okay, this is where you can have hydrogen bonding. This is where you can have dipole-dipole interactions. Okay? This is the one that has the highest. It's called methanol. It has the strongest hydrogen bonds of the available choices. All right? Although fluorine is more electronegative than oxygen, there were no HFs. There was hydrogen bonding with the nitrogen, but O was next on your list. For hydrogen bonding to happen, the hydrogen has to be with N, O, or F. Okay? But that doesn't just mean it's in the thing. It means it has to be bonded to it. That's why the second option we had was incorrect. Okay? So, there we go. Questions about that? Yes? Say that one more time. No, it doesn't have to. We're just saying this is going to have the highest boiling and melting point because it does have OH. But yes, it's harder to melt with hydrogen bonding because hydrogen bonding is the strongest dipole-dipole interaction, which means it holds it tighter, which means it's harder to break it apart or to melt it. Okay, we have one more. Okay, fine. It is. Well, this is 1998 right here. And by the way, like having links, they were called anchor links or something like that. Like those were lit back then. Like this dude knows what he's doing because every single part of this was written in code. Now we don't. We have Wysiwygs. Does anyone know what that is? Wysiwyg is what you see is what you get. And you just drag things in and you make your website. The person that made this typed out literally every piece of code or her code by themselves. So it looks crappy, but if you knew how hard it was to do, it wouldn't be that crappy. Okay, short discussion. Try number 2, if you would. Number 2, we can get a smiley emoji a little bit sooner. All right, so here we go. Raise your hands if you think A is the correct answer to this. Okay, that's a lot. B. 1 B, 2 Bs, 3 Bs. C. And D. All right, 1 D. All right, so here we go. Oh, A was the smiley face. A, so the majority, that's good. You are correct. This is like so rewarding. I like the emojis. All right, you are correct. The attractive interaction between alkanes are dispersion forces, right? How did we know this was an alkane, by the way? There's no double bonds. Is there anything besides a C and an H? No. So really, all the considerations we had to look at here, they were thrown out. And all you had to do was compare their shape and size, essentially, right? So they were alkanes because there was no double bonds. Back to the emoji. All right? Between alkanes are dispersion forces, which are rapidly fluctuating weak dipoles of the carbon-hydrogen bonds, as shown in the following illustration. It doesn't really say why, but it's more easily polarized because there's more surface area. Did anyone use the word surface area in a discussion or their thinking process? Okay. I drew this out yesterday, 1, 2, 3, 4, 5. So I drew it yesterday as well. That's going to be 6, huh? 1, 2, 3, 4, 5, 6, whatever. Just pretend that if we did it this way, my fault for drawing a hexagon and not a pentagon, but whatever. Then they would only interact 2 to 2, essentially. All right, instead of 1, 2, 3, 4, 5 to 5. greater surface area for the opportunity for these temporary dipoles to be created. Sound okay? Okay. Question's correct. These are written in order of strength. Hydrogen bonding, greatest. Dipole-dipole, next greatest. London dispersion, the weakest. Okay? Fair enough? Okay. Let's move to the next idea here. Here's just a summary once again. It's not super easy to see, I guess, with the contrast. But it's just a little flow chart you can use to figure out what type of thing is involved here. We don't usually, like in this class, we don't talk about ion dipole very often. And it's not because it's not important. It's because it's just the easiest to see. If you have an ionic substance, you're going to go. So the way this chart works says, are there ions involved? If so, your second check is, are there polar things? If no, then we're to lattice energy, which we learned a while ago, or ionic bonding. Okay? Ionic bonding has the highest intermolecular forces of all, and we call it lattice energy, which was a different chapter. Okay? It was the attraction of the actual ions. Okay, if there are ions and polar substances, then ion dipole. Okay, if there were no ions, then you check, are there polar involved? If the answer is yes, then you need to check, is there hydrogen bonded to NO or F? If the answer is yes, you have hydrogen bonding. You also would have dipole-dipole. All right. If it's no, you have dipole-dipole. And then if everything's no, then you're just stuck with London dispersion forces. Please remember, every single one of them have London dispersion forces. All right? But their importance in the actual compound itself decreases a ton as you move from right to left. If you have a lattice energy that requires thousands of joules to separate it, and the LDF is like 0.2, we're not going to care. You all right with that? We don't care about them. They're not that important. Not that important. Not that important. A little bit important. And the only important part. Okay? But they are in every single thing. Just not the most important part. Okay. Now, some of the vocabulary terms that we got to do. Hold on. Uh-oh. So, intermolecular forces affect many physical properties. We've already talked about boiling and melting point a ton, so hopefully we should know that. All right? So, the strength of the attraction between particles greatly affects the properties of a substance or solution. All right? Viscosity. Is that one of the terms you had to learn? I think it was one of the vocab ones. The resistance of a liquid to flow is called viscosity. Okay, what I would have you do is on the computer, but I'm just not going to have you do it. Because then your mouse and my mouse would fight. So just hang out on your phone over there. All right, so like when I was a kid, this was an easy word to know. Everyone knew it because you watched TV and it would talk about Pennzoil and how it would protect your engine and prevent viscosity issues. All right? And thermal breakdown. Like that was their line. Prevents viscosity and thermal breakdown. All right? So viscosity is basically how well something flows. All right? It is related to the ease in which molecules can move past each other. You are used to viscosity because you get syrup, right? Your syrup flows well when it's warm, and it flows very poorly when it's cold. All right? Viscosity increases with stronger molecular or intermolecular forces and decreases with higher temperature. Now, I've never, ever seen a test or AP test have a question like where it says, which of the following is the most viscous solution? By the way, high viscosity means it does not flow well. Okay? Low viscosity means it does flow well. Okay? But knowing what viscosity is, that is important. You got to go, Perry? Okay. You're freaking me out. The bell's ringing, but I think I still have 10 minutes. All right? So the reason Pennzoil, which makes oil, would have this in their commercial is they were saying that their oil flows well, which is what you want in your car engine. Even when it's cold, you want the engine to, or the oil to still flow and lubricate the parts. So that's why it was in their ads. Okay, so viscosity, resistance of a liquid to flow. High viscosity, low flow, low viscosity, high flow. Okay with that? Okay. Surface tension. These were my favorite. Like, I am old, so I grew up in Vernal, Utah with no TV. From 0 to 12, I didn't have a TV. I didn't have the internet because it didn't exist until I was off my mission. I didn't have a Nintendo until I was like 14. Anyway, I played outside, and I played in a ditch in the summer, which, now that I think back, was gross. Like, we would get leeches on our legs, and we wouldn't even care. We just pull them off. And now I'm like, that's pretty gross. But man, we had fun in that ditch. And we would play with the Jesus bugs all day long. All right? They have a specific name, but we call them Jesus bugs because they could walk on water. Okay? The reason they can is because surface tension. All right? Surface tension exists because of intermolecular forces. Surface tension results from the net inward force experienced by the molecules on the surface of the liquid. Now, not that you should, but does anyone know how to kill all of the Jesus bugs? Put soap on the water. You could put gasoline on the water as well, which you shouldn't do, especially in the ditch that waters all the crops. But it was kind of cool. You could just drop a few drops of soap, and in that little area, they're like, bloop! Because what did the soap do? It destroys the surface tension. Now, the water still has a lot of mass, so that bug would still be on top, but not its legs. Like, it would just be like a bug floating on the water, but not walking around on the water. It was neat. We didn't do it very often, but it was like really cool. Like, why did this even happen? But it did. Okay. You all right with that? Okay. Surface tension. That's the resistance from the inward force of things flowing downward into it. In probably like 5th grade, you floated a paperclip on water. You tried. Some paper clips are coated in plastic, and it makes it way harder to do. It was easier to do 25 years ago when they were just a piece of metal. All right. Well, if you did that, that was because of surface tension. All right. Phase changes are affected by intermolecular forces, which we've already talked about. All right. The higher the intermolecular force, the harder it is to make something a liquid or a gas. Okay. The reason this is up here, I don't know that these were vocabulary terms, but these are words you should just kind of know, and most of them aren't hard. All right? When you have your solid, liquid, gas, when phases change, they have names. We've used these a lot in your life. When a solid goes to a liquid, it melts. When a liquid moves to a solid, it freezes. When a liquid goes to a gas, typically you've called it boiling, but the more technical term is vaporization, which isn't too hard, hopefully. Turning a water to a gas, you're making it water vapor. All right? You've probably used this term in your life before. When a gas becomes a liquid, we call it condensation. No. Well, okay, so when you condense things, you make them close. When you condense the milk, you're getting rid of the water and you're keeping all the fats and sugars. So Yeah, like the idea of condense is related, but I mean they're not specifically. No. All right. These are the only two words that you may not be familiar with. You definitely need to be familiar with sublimation. Okay, that's a key word. Sublimation is what dry ice does. We call dry ice because it doesn't exist as a liquid. It's either a solid or a gas. And that's because carbon dioxide at 1 atm, it doesn't exist as a liquid. It exists as a gas. So we take this really cold substance, we put it in our coolers that you don't screw the lid on, okay? And then you let this process happen, and it's called sublimation. More than one person has blown up their root beer cooler. Like, I don't get it. Like, at least one person in this room maybe has blown up a root beer cooler. When you dump that dry ice in to make your root beer, it has to be, the lid has to be off. All right. Then, you can look at it that way. Deposition is when your gas becomes a solid. It's the reverse of sublimation. We don't talk about deposition as much as sublimation, but all right. Heat of fusion. Was that one of your terms? I know that this chapter is just a lot of vocab, but it just is. Like I can't control that. Heat of fusion is the energy required to change a solid at its melting point to a liquid. Okay? And it's definitely 100% tied to the intermolecular forces. The greater the intermolecular forces, the greater the heat of fusion, meaning the more energy you have to put in to break the things down. All right, now, what is interesting about this? I can't make this very big. We're going to zoom way in. I'll leave that definition right there. All right. What is interesting here is the difference in size between the purple and the blue. Yep. It's official. Trivia Crack has made a comeback. It was so cool like 10 years ago, and then it died. And now it's alive again. Trivia Crack. The game you're playing. The game 3 kids asked me for help yesterday in class. All right. So, the heat of vaporization is pretty much the energy to boil it. And the heat of fusion is essentially the energy to melt it. Okay? Now, based on this graph, we can learn something that is important to know. It takes way more energy to boil something and completely convert it to a gas than to melt it. And I want you to have a discussion. Why does it take way more energy to do this than it does that? This is a test question. So have this discussion and we'll discuss it. Intermolecular forces. And so then he said in a gas you completely disconnect. What word did you use? Disrupt. Okay. He's right in a lot of ways. So here we go. When my solid breaks down into a liquid, whatever, I don't even know how to draw that. We'll call this a liquid. There are still some attractive forces between these molecules. We know there are because it's a liquid. Okay? These things are still attracted to each other. Are you okay with that? But in a gas, okay, we'll pretend this is a balloon now. Are these particles attracted to each other in any way? No. In a gas, let me say this again. To move from a liquid to a gas, you have to break every single attractive force. They all have to be broken. Every individual part has to be separate, and there is no attraction left. But just going from a solid to a liquid, you are weakening the intermolecular forces, but they're all still there. Okay? But to make something a gas, all intermolecular forces must be overcome. And the way we do that is by adding energy or heat. Are you okay with that explanation? Okay? So we can see it here in this graph. To make butane a liquid, it didn't take that much energy. To make butane all of a gas, it takes roughly 5 times the amount of energy it did before. Now to us, butane's already a gas, but like we're saying, from where it wasn't. All right? Diethyl ether. This is the stuff you spray in your car engine to make it start, if anyone ever has done that. 7 and 29. Water, 6 and 41. All right? Mercury, 23 and 58. Okay. It takes different amounts of energy to boil or vaporize something than it does to just melt it. All right. So heat of vaporization. I guess I should have done this slide first, but we already pretty much said it. Energy required to change a liquid at its boiling point to a gas. I feel like Jansen's ruining multiple people's... The bird? I have no idea. It's something holding a worm. All right. Are we good with this? Are we good with heat of vaporization? Okay. Next. This is the heating curve for water. This is sort of the same exact thing we just looked at in a different format. If you had regular chemistry, this is one of the few days where it's the same thing as we did before. This, you're taking a piece of ice and you're converting it to a gas. And then you're just keeping track of its temperature versus the energy added. Okay? So you put energy in and your ice warms up. And then once ice gets to 0, it melts. But do you notice this line is flat? While ice is still present, the water is still just barely above the melting point. So as long as I have ice in here, which I do, the water in here is going to be just barely above the melting point. Okay? Because any heat that goes into the water between here and here, what is it doing? It's going into the ice to melt it. All right? That's the heat of fusion. Right? It's represented here. 1 second. Up here, this line's a lot longer. That's the heat of vaporization. It took more energy. Okay, go ahead. Yeah, it is. You just have to keep it completely still, changing no pressure or vibrational energies at all. You can super chill it, and then once it's disturbed, yes, it goes straight to ice. It happens in your water bottles, like occasionally. My pops do it once in a while if they're real cold. I'll open them, and like my first drink's liquid, and then like a minute later you look and slush has come out the top. Has anyone ever had that happen? All right, so yes, it is possible. Okay, now, once all the ice is gone, all the energy just goes into heating the water. That's why your drink gets real warm real fast once the ice is gone. And then we'll pick it up. So we didn't finish. We definitely will finish chapter 11 tomorrow.